So last section we're going to look at is 11.1. Totally different than solving systems. It's on what we call sequences. So the idea of a sequence is that you have a list of numbers and there is some type of order to those numbers. And the goal is generally to figure out a pattern for the sequence. So that way if I said to you, okay, here's the first 5 numbers in the sequence, tell me the 98th number. So generally, if we can find a pattern, that's not that hard of a question to answer. If we can't figure out a formula for the pattern, then it's not an easy question. So generally, when we are talking about a sequence of numbers, I will refer to the sequence using a lowercase English letter. Okay? Like the sequence I'm about to show you, I'm going to call it sequence B. This particular sequence has 4 terms given. A dot, dot, dot means there's an arbitrary amount more, but then it stops somewhere. Okay, I know that this particular sequence stops because it doesn't end with a dot, dot, dot. It ends with B sub n. Well, where does that stop? Is that like 5 more terms away or 20 more terms away? I don't know. But I know that it stops somewhere. It could be 1,000,000 more terms in this dot, dot, dot. But it stops. When you want to refer to a particular number in a sequence, you use a subscript. B sub 1 means the first number in sequence B, which in this case is right there. B sub 2 means the second number. B sub 4 would be that number. Okay, so that's the notation for describing a particular term in your sequence. Okay, and there's a pattern to those numbers. Those aren't, they're not random. There's a way I'm getting the number that I'm showing you in that sequence. So in order for a sequence to be unique, there has to be a formula to calculate the terms in it. So in order for a sequence to be uniquely determined, there has to be some rule that's giving you the terms. And generally, for a particular sequence, like sequence B, there is one rule that will give you that formula. Well, technically there's 2. We're going to talk about explicit versus recursive. But if we're talking about explicit, there is one rule that would give you that formula. Now, if 2 people come up with different formulas for the same sequence, then one of 2 things happened. Either one of you made a mistake because you should come up with the same formula, or you really have the same formula, but you each wrote it a different way. Kind of like writing something like this versus writing like this. Those aren't different. They're exactly the same thing. You just wrote it differently. But in general, we're each going to be finding the same formula. And the goal when you find it is we will simplify it as much as we can. Right? So let's look at this sequence. Does this look like a sequence that stops somewhere or a sequence that would go on forever?
Go on forever?
Yeah, this one goes on forever. This is different than the last one. The last one had a final term somewhere. Where's the final term? It's the nth term. I don't know what the nth term is. Maybe it's the millionth term, but it does stop. This one has a bunch of terms. It has an nth term somewhere down the line, and then there's even more after that. So there's no end to this sequence. Okay, that's called an infinite sequence. Infinite means it goes on forever. So what I would like to do is see if we can come up with a pattern for the sequence. Generally, to come up with a pattern, you have to know the first 3 or 4 numbers. If I only gave you the first 2, that's not enough information to figure out the pattern. There's a lot of ways I could get from 2 to 5. I could say maybe the pattern is you take this number and double it and add 1. Because if you double 2, it's 4, plus 1 is 5. But doubling 5 and adding 1 is not how you get to 8. So there's a different pattern going on here. Does anybody see what the pattern is? Yeah.
Plus 3.
Okay, what can you be more specific? Like plus 3 to what?
Well, x plus 3 then, or n plus 3, technically.
Can you describe what you mean by n? Like you say plus 3, but what are you plussing 3 to? Like if you wanted to describe it in words.
The variable that you're given plus 3.
Well, here you're given a 2, a 5, an 8, and an 11. So you're given 4 numbers. So we're not really given any variables there. Just 2, 5, 8, 11. So let's talk more about the plus 3, but we just need to describe like plus 3 to what? Yeah?
What I got was 3n minus 1.
Okay, that's different. So right now we're talking about plus 3. We'll come back to
Taking your
that.
current number and adding 3 to it on each step.
Take the.
So it's 2 plus 3 to get to 5, plus
Okay.
3 to 8, plus 3
Yeah.
to get to 11, and then so on.
So how did you get, let's talk about this one. How do you get 5? Yeah?
You add 3 to your last term.
You add 3 to the one that comes before the one that you're looking for. Yeah. So add 3 to the one that's before. So this is the actual term. Let's put the position of the term underneath it. First one, second one, third, fourth.
A1 plus 3 to
So-
n power.
That's what we're doing.
So to get the second term, you added 3 to the one that came before it.
Yeah.
How do you write, if this was our term, how do you write the one that comes before it?
An minus 1.
Yes. So that is one way to write the formula. This means to get any term that you want, take the one that comes before it and add 3. So let's say we wanted to find out when n is 50. If n is 50, that's a sub 50. What term do I add 3 to get the 50th term? Yeah.
A sub 49.
50 minus 1, which is the 49th term. That's how you get the 50th term. Okay. Was I given the 49th term in that equation? No. So now, in order to get the 50th term, I need to know the 49th term. How do you get the 49th term?
A 48 plus 3.
Okay, take the 48 minus 1, oh, I'm sorry, 49 minus 1, that's the 48th term, and you add 3 to it. But were we given the 48th term? No. So we're going to have, if we do it this way, we're going to have to go all the way back to get the 50th term, all the way back, 49, 48, 47, all the way down to the first term. This type of formula, while it is correct, it's not the best way to do it, right? Because it relies on knowing every single term up to the one you're trying to find. A better way to do it would be, is there a formula we can plug in a 4 to, and it automatically just gives us an 11? Or is there a formula we can plug 3 into, and it automatically gives us 8? I'd rather focus on where the term is, its position, than use the one that came before it. Yeah, using the one that comes before it, never a good idea. So does anyone see a different way that we could calculate our terms? Yep.
3n minus 1.
Yeah, you could do the formula 3n minus 1. And what this means is if you are looking for a particular term, like the 50th term, you triple the number 50 and you minus 1. So it would be 149. So very, very quick way to get the 50th term. And we can check it with a couple. Plug in 4. What's 3 times 4?
12,
Minus 1?
11.
There's your 11. Check it with 3. 3 times 3 is 9. Minus 1?
8.
There's your 8. Right? This is called a recursive formula on the left, in the red box. The one on the right is explicit. Generally, an explicit formula is harder to figure out. But once you figure it out, it's much easier to use. Okay? Recursive, very simple to figure out the formula, not very useful because of this concept right here. So I'll write that down, but this is more what we're going to try to focus on doing, explicit formulas. Right? And if you're like, well, how did he see that? Then you just take this number and you triple it and you subtract 1. Well, there's a way that for some formulas we can kind of use some hints to figure this out. Some are very hard. Like if you had a sequence where you had to take the number, square it, multiply it by 5, and then subtract 8. I mean, that's a hard formula to figure out. There's a lot of steps to it. But if I have you figure one out, it's generally going to be like multiplying it by a number and then adding or subtracting a number. It's going to be like a 2-step. I guess, yeah, like 2 steps in the formula. So now I started to talk a little bit about whether a sequence ends in a ... or it doesn't. If it ends in a ... it is an infinite sequence. It means it goes on forever. That means when you are using this formula right here, you can plug in any integer you want for n. Positive integer. N represents the position. Like first position, second, third, fourth. Why wouldn't you plug in a decimal for n?
Because you can't have like a decimal spot, I guess.
Yeah, you can't have a decimal position. It's like people finishing a race and like who finishes first, second, and third. Nobody finishes in 2.5th place. Your first place or your second place. There's nothing in between 1 and 2. Same thing here. That's why when we fill numbers into these formulas, you have to fill in integers. You also can't fill in negative integers. There's no such thing as 0th place or negative first place, negative second place. No, you're in the first spot, second spot, third spot. Okay, so there has to be a positive integer you fill in. And if it goes on forever, you can go as high as you want. You want to know what the 10 millionth term will be? Well, it's going to hit a 10 millionth term eventually because there's a ... It goes on forever. Comparing that to a finite sequence, the domain or the numbers that you are allowed to fill in right here are not every positive integer. It's only some of them. Because at some point, your formula stops. So if we had a formula that generated the terms in this sequence, could I plug in 10 million? I don't know. There's no ... so there's a limit as to how high this one went. Maybe it doesn't go to 10 million. Maybe it only goes up to 100. So the last term is a 100. I don't know what the last term is, but there is a last term at some point. So when you have a finite sequence and you have a formula for it, you are not allowed to plug in numbers as high as you want to go. You can only plug in as high as the number of terms you have. Okay? Going beyond that doesn't make sense. Right, so any question on the difference between an infinite sequence and a finite sequence? Okay. So let's see if we can just, by being given a formula, I'm not saying you'd have to figure this one out, because that's kind of a complicated formula. but I want to know the first 3 terms, and then I want to know the 15th term. Now, looking at the formula that I wrote down, does it have this in it? A sub n minus 1. No, it doesn't have that, which means that's good. Okay? If you want to find a particular term, you do not need to know the one that comes before it, because you don't have this in it. You can find any term you want to know directly by plugging in that position. So let's start with the first term. If I want to find the first term in that sequence, what number would I plug in for 1? 1. What's 1 squared? 1 minus 1 divided by 1. So what's going to be my first term in that sequence? 0. Yep. What number would I plug in for n if I want to find the second term?
2.
Plug in 2. What's 2 squared?
4.
4 minus 1. Again, I'm just filling in 2 for both my ends.
3 halves.
That's going to give me 3 halves. Okay, let's find the third term. What's 3 squared?
9.
And 9 minus 1?
8.
So that's 8 thirds. And the 15th term. What's 15 squared?
225.
225. Minus 1. 224. And what goes in the bottom?
15.
Whatever number you're looking for. We're looking for the 15th one. Okay, so that's how you use a formula to predict or calculate terms in a sequence. If you're given the formula, that's pretty straightforward. Any question how we got the first 3 terms and then the 15th term? Now, when I got the 15th term, did I find every one in between the 3rd and the 15th? No, I was able to skip them all because I didn't have that in the formula. If I had had that, this would have been a lot more work. Okay. But we didn't. So that type of formula that I just showed you, I think I mentioned this already, that's called an explicit formula. An explicit formula is the one that you want to try to find. Is it harder to find? Yeah. But is it more useful? Yeah. So explicit formulas allow you to calculate any term you want to know in the sequence directly. You don't have to find anything other than the one you want to know. Did anybody remember what I said the other kind was called?
Recursive.
Recursive. Okay, recursive formula, again, easier to find, not very useful. Because if you were using a recursive formula, and I said to you to find the 900th term, you'd have to know the 899th term. And if you didn't know the 899th term, you'd have to find the 898th term, and 897. Every single term, all the way back to the beginning. Not bad for like a computer. You could definitely program a computer with a recursive formula, and it would still be able to find a term pretty quick. But even a computer, like if you wanted to find like the 10 trillionth term of something very complicated, and the computer had to calculate every single term from the first one to the 10 trillionth one, depending on the complexity, that could take the computer a while to figure out. So explicit formulas are always much more efficient. Here's an example of a recursive formula. In a recursive formula, I have to start you off with something. Generally the first term. If you do not know the first term, and all I give you is take the one before it and add 3, well, then you're kind of stuck. You need to be able to start somewhere. So the first term is 2, and the reason I know that, given. Okay, it's given. What would be my second term using the formula that's right here?
4. 5.
5. What does that, if somebody looked at that box and they didn't understand this notation,
Because it looks like you're taking the last term and subtracting 1, but it actually is just referring to the last term at the end, the an minus 1.
yeah, so what does this really mean to do? Just like if you put it in a sentence for someone to understand very easily.
3 plus the last term.
3 plus the last term, that's what it means. Take 3 plus the one that comes before. So if you want the second term, add 3 to 2. What about the third term?
Add 3 to 5, so 8.
Add 3 to 5, so we get 8. And now if I wanted to jump all the way to the 100th term, I'd take the 99th term and add 3. But I don't know that one, so then I have to find that one, which is the 98th term, plus 3. So I'd have to go through all those numbers. Okay, so any question on the difference between explicit and recursive? Yeah.
Do all recursive formulas have an explicit version as well, or no?
So it's a good question. Most of them do. I'm trying to think if there's any that might not. I don't know if you could make one that would. I'm not sure. Some of them are very challenging to figure out. Like even if I did one like let's say I did this. Let's say I start with 3, and then let's say I did this, and then let me do one more. There is a pattern to those numbers, but I don't know if anyone's going to be able to figure out what I did to get that, right? And it's not even that, in terms of complex, that's not even that complex. Does anybody see how I got those numbers?
3n times 2 squared.
What did I do?
3n times 2 squared.
3n times
Wait, no, that one.
3n times 2. So that means
Wait,
6
that'd just be n.
squared. You said 3n times
3n. Oh, it's just 3n squared?
No, I don't do anything with tripling.
Oh.
I doubled it and I squared it.
Okay.
So if you double
So
3, you
6
get
times
6.
6, yeah.
And 6 squared is 36.
Oh.
36 doubled is 72. And then 72 squared was 5184. So I doubled it and I squared it. So that's not even that complex, but it still is pretty hard if you don't know how I got that. Another one we'll talk about in a minute, I'm going to hold off for now, is even harder than that. But I guarantee it's a sequence you've seen before. All right, so let's look at this one. Determine the first 4 terms and the 8th term. So I made a table for everything. What's going to be the first term?
2.
2. And how did you figure that out?
Well, term is right there.
It's
A1.
given. Yeah. So recursive sequence has to be given. Now, in kind of very simple language, what does this mean to do?
Add 4 to the last term.
Add 4 to the one that, came right before it. So the second term would be how much?
6,
6. And the third term?
10,
10. And the fourth term?
14.
Now, those are the only 4 in a row that they wanted to know. Now they want me to jump to the 8th term. Can I jump directly to the 8th term? No. I need the 7th, the 6th, and the 5th. So I have to continue this pattern because it's recursive. So they want those, and then this. What would the 5th term be? 18. 18, and the 6th?
22,
22, and the 7th?
26,
and the 8th.
30. Would you be able to just do 4 times 4 and add it to the 4th term, since you're just adding 4 each time?
So yeah, you could kind of figure out how many times you're adding 4.
And just
then
multiply it instead of
multiply
doing
it.
each individual term?
Yeah. It would be even better if we realized what the pattern is, which is times 4 minus 2. What's 8 times 4?
32.
And what's 32 minus 2?
30.
30. Right? Let's try it again. What's 4 times 4?
16.
Minus 2.
14.
So the pattern is times 4 minus 2. So if I wanted to know the 1,000th term, I don't even have to figure out, oh wait, I added 4 996 times. I don't even know how many times you add 4 to get to that. But all I have to do is say it's times 4 minus 2. 4,000 minus 2. That's the answer. 3,998. That's the 1,000th term. All right. And how did I figure out to multiply this by 4 and minus 2? Well, the patterns that they work with in this section are generally just multiplying by a number and then adding or subtracting. So that's how I figured it out. All right, let's try this one. So now we're going to take an explicit or recursive formula and make it explicit. Okay, so the pattern is adding 5 to the one that comes before, and we're starting with 3. When you want to make something explicit, it's generally helpful to write out the first few, so then you can look at it. What would the second term be in this sequence?
8.
8, and the third term?
13.
13. And let's do it more. What's the fourth term?
18.
18. Okay, so to make this explicit, the goal is to look at the position and turn that into the number 3. Or how can you turn 2 into 8? How can you make 3 into 13? So you got to find a formula you can plug in this number and get that number.
4. Yeah, you would multiply by 4 and then subtract 1. No, you square the number and then add 2.
Well, if you square this number, you get 4, and then you'd have to add 4 to get to 8. But then if you square this number, you get 16, and you only have to add 2. So squaring it this time is not going to be the pattern. Generally, like I said, it's usually multiplying by something and adding or subtracting. Yeah.
Multiply the term by 5 and subtract 2.
Yeah. The pattern here is times 5 minus 2. 3 times 5 is 15. Minus 2 is 13. 4 times 5 is 20. Minus 2 is 18. So the pattern is 5n minus 2. That's the explicit version. That's the recursive version. Okay. Any question on that one? Okay. So here's another sequence which maybe you've heard of, or maybe not. It's called the Fibonacci sequence. And the Fibonacci sequence is a very popular recursive sequence that does have an explicit formula. Bless you. It's much more advanced math to figure out the recursive formula. It is not just like adding, 5 and times 2 or something. It's pretty complex. So we never look at the explicit formula for this. But we do look at the recursive because it's much easier. Okay. What in simple language is this telling me to do to get a particular term?
Add the last term and the term before that.
Right.
To get your new term.
It's telling me to add the 2 terms before the one that I have to get the next one. So because it relies on not only the term before, but the term before that, I need to start you off with 2 numbers. Okay. So the first 2 terms in the Fibonacci sequence are 1 and 1. what would be the next number after that?
Equals 5n minus 2.
Third term would be 2,
Yep, third one would be 2.
3,
And then 1 plus 2 gives you 3.
5,
2 and 3 is 5.
8.
8, how many did they want? The first 6. All right, so we're done.
does it have an explicit formula?
What's that?
You said it has an explicit formula?
Yeah, there is a formula. So like if you wanted the 200th Fibonacci number, right now you'd have to keep going, 5 plus 8, get that, and then keep going. But there is a formula. Again, not super easy to come up with. And it's very different than the kind of formulas I've been showing you so far.
Do you know it?
I did at one point, but not off the top of my head right now.
Oh, all right.
Yeah. I think it was something I looked at. It was definitely either undergrad or graduate school. It wasn't high school. Yeah. So that's it. There's your Fibonacci numbers. Any question on that one? And then Fibonacci numbers can be very useful, especially if you're ever in an escape room and the backs of the paintings have the Fibonacci numbers on them, but they're up in the thousands. And if you're a teacher and you don't normally teach the numbers that are up in 1,000, you might not recognize the pattern, and then you'll feel really bad after that you didn't get the pattern because you're a math teacher and you didn't recognize Fibonacci numbers in the thousands.
This is the Fibonacci explicit sequence.
Oh, you found it. Yeah, it's pretty advanced. Yeah, that is a true story.
1 divided by the square root of 5 times 1 plus the square root of 5 over 2 to the power of n minus 1 divided by the square root of 5 times 1 minus the square root of 5 over 2 to the power of n.
Yeah, it's
You don't
pretty,
have that memorized?
it's pretty complex. No, I don't.
No.
Yeah, so it's a very advanced one. All right, so the two special kind of sequences that we're going to look at either have to do with adding the same number to get from one to the next. So in this case, it's like plus 5, plus 5, plus 5 over and over. Or we could look at a sequence like this. What's happening in this sequence?
You're doubling last one.
Yeah, we're multiplying by a number over and over. Okay. If you are adding a number over and over, or multiplying by a number over and over, those are very easy sequences to come up with formulas for. You can see with the Fibonacci sequence, you're not doing either. You're not, like here you add 1, then you add 2. I'm sorry, you add 1, then you add 2, then you add 3, then you, so what you're adding each time is changing. And you're not multiplying by the same thing. Like here you multiply by 2, 1 times 2. But then you don't multiply by 2 again. It keeps changing. So this wouldn't fit either thing that I'm about to show you. Hence, it's a much more complicated formula. So an arithmetic sequence, okay, or you can also call it an arithmetic progression. Sequence and progression, they're synonyms, is when you add the same number over and over. So that number that you add repeatedly, they call it a common difference. So why do they call it a difference if it's what you're adding each time? Oh, so let me, that's not going to work. Let's do like 2 plus 5 is 3, 8, 11. What did I add each time? I added 3. What's 14 minus 11? 3. 11 minus 8? 3. So they call it a common difference because if you take any term and find the difference with the one before it, it will be the same. It will be common for everything. Take a term, subtract the one that's before it, it will always be 3. So 3 is called the common difference. And if you have a pattern where you add or subtract the same thing over and over, that is the explicit formula. So you need to know two things to write the explicit formula. First thing you need to know is the very first term in the sequence. The next thing you need to know is D. D is the common difference. It's what you're adding or subtracting repeatedly. As long as you know the first term and what you're adding or subtracting, I can very easily come up with a formula for this. This one would be 2 plus n minus 1 times 3. That's the formula that will predict those numbers. Let's try it. See if it works to predict the fifth number. What's 5 minus 1?
4.
4. What's 4 times 3?
12.
And 12 plus 2?
14.
There you go, 14. So that formula will predict these numbers if you plug in the number above it. That's the position. All right, let's try that on one that we did earlier. Okay, this just means you have to plug in an integer. Remember, it's the capital Z. That's the symbol for an integer. You cannot plug in a decimal in this formula. I mean, you can, but the number has no meaning. Right? There's a third term and there's a fourth term. There's no 3.5th term or anything like that. So the first term plus n minus 1 times d. Let's go back to this one. So we were able to figure out a formula. We were adding the same thing over and over. But whoever figured it out, they just kind of looked at it. They said, it looks like times 5 minus 2. Right? They didn't really use any math to do it. Okay, now let's use that formula. So it's the first term plus n minus 1 times d. So this gives you a concrete set of steps to figure it out. What's the first term in that sequence?
3.
3 plus, and what's the common difference between this number and that number?
5.
5. Okay. Does that look exactly like that right now?
No.
No, but let's simplify that and see what we get. Distribute the 5. What's 5 times n? 5n. And what's 5 times negative 1? Negative 5. Now combine like terms. What's 3 minus 5? Negative 2. That's exactly the same formula that we got. This was just looking at it and trying to figure it out. This was following a set of steps to figure it out. Okay, any question on that? All right, so let's try this one. Let's find an explicit formula for that. Yeah.
Just a question on the last one. Where did you get the 5 from again?
The 5, that was the common difference. So it's what we were adding each time to get from one number to the next. Okay. Thoughts on example 5 before we start?
We don't know what the first term.
We don't know the first term. That's impossible. You can't solve that problem the way it is. Okay, I need to start you with the first term. So what do we want to make the first term? Just don't make it a 3, because then you have another 3 and there's too many 3s.
1.
We'll make it a 1. Make it a 1. All right. So what I would do to find an explicit formula is let's just write out the first couple terms. So once we get our formula, we can check it and make sure it works. What would the second and third terms be based on that?
4 and 8, or 4 and 7.
4 and 7. All right, so we know those are right. Right, just double check that you added 3. So once we get our formula, we'll check it. Okay, when you are writing an explicit formula for an arithmetic sequence, what's the first thing that comes after the equal sign?
The first term.
First term. And in this case, that is
1.
1. Okay. After that, we put plus, and what comes next?
N minus 1.
N minus 1. and on the outside of the parentheses,
Times the difference.
times the common difference. So look at a term, subtract the one that comes before it. What do you always get?
3.
3. It's always that number right there. Okay, so simplify that. What's 3 times n?
3n
3n. What's 3 times negative 1?
minus 3.
Minus 3 plus 1.
Minus 2.
Minus 2. So that should be our formula. Let's check. If we plug in 3, we should get 7. What's 3 times 3?
9.
9, and minus 2 is 7. If you plug in 2, what's 3 times 2?
6.
6 minus 2.
4.
There you go. Yep. So that's the explicit formula from that recursive formula. Any question on that one? Okay. So this one says the first 2 terms in the sequence are negative 8 and negative 2. Find the, just change that. Find the explicit formula and the 100th term. So without the explicit formula, then we got to kind of figure out, okay, what are we adding each time? How many times do we do? There's too much to think about. So let's see if we can find the explicit formula, and then the 100th term should be almost instant. Okay. What's the first thing I'm going to put down for my explicit formula?
First term, negative
First
8.
term, negative 8. And what comes after that?
N minus 1.
Before the n minus 1.
Parentheses.
Before that.
Plus.
Plus. Then n minus 1.
And then the common difference on
Okay.
the outside. So
Yeah, so we got to figure out, we don't know what we're adding. They didn't tell us. But you can figure it out by taking this term and subtracting the one that comes before it. Okay, you are adding 6 each time. Any question why you're adding 6? So simplify that. 6 times n gives me
6n.
6n. 6 times negative 1,
Negative 6.
negative 6, plus negative 8,
Negative 14.
negative 14. Okay. So that's the formula. Now, what's the 100th term?
600 minus 14.
586.
Yeah, 586.
586, yep. So take 100, plug it in. 600, take away 14. 586. All right, any question on that one? Yeah,
Where you get the 6 from?
the 6. So the 6 on the outside, that's the common difference. It's what you add each time to get from one term to the next. Yep. Okay, what are we missing in this one that's very important if we're trying to find a formula?
First term.
We don't know the first term. Bless you. But you've got enough information to figure it out. Look at from 13 to 3. How many units are there between 13 and 3, like on a number line?
10.
There's 10 units. You're traveling 10 units in 5 jumps. Each jump has to be equal.
So 2 units per jump.
So each jump is 2 units. So that allows you to fill all of those in between. But we want to go backwards now to get the first term. So we subtract 2 each time. So how would we go backwards?
Add 2.
We'd add 2. And the first term?
17.
There you go. So now your explicit formula is the first term plus n minus 1. And what do you do? The d is what you do as you go this way.
So negative 2.
Negative 2. You are subtracting 2 each time. You read it left to right. Any question why it's subtracting 2, not adding 2? Okay, and then you could simplify that, but I'm going to leave it like that. Okay, any question on that? All right, so those are the ones where you are adding the same number each time. What did I say the last pattern was going to be? It's where instead of adding each time, you multiply. Yep. So in a geometric sequence, it's where you multiply each number by the same thing over and over, like this. That is a geometric sequence. I'm multiplying by 2 each time. And the way you can figure out what you're multiplying by each time is take any term in the sequence and divide by the one that comes before it. What's 12 divided by 6?
2.
2. What's 6 divided by 3?
2.
2. 24 divided by 12?
2.
2. It's always going to come out to 2. And when a fraction always comes out to the same thing, that's called a ratio. Right? Ratio is a fraction. So if you take any term and divide by the one that comes before it, and it comes out the same, then you have a geometric sequence. Now, recursive, it's a very simple idea. Just take the term that comes before the one you want and multiply it by r. That's all you're doing. But we don't want that. We don't want that minus 1 there, right? That's recursive. It makes it complex. So if I said to you, what's the 500th term here? Well, you got to figure out, okay, I got to double it, what, 496 more times or something, right? We don't want to have to think of it that way. So for a geometric sequence, this is the formula to calculate any term you want to know explicitly. Okay, this is just a hint how to find r if you're not sure. Take a term and divide by the one that comes before it. So let's try that for this one. So you still need to know the first term. That's important. First term is 3. R is what I multiply by each time. What did I multiply by each time?
2.
2 to the n minus 1. That should be the formula. Let's see. Let's try it for 4. If I fill in 4, what's 4 minus 1?
3.
3. What's 2 to the third power?
8.
8. And what's 8 times 3? There you go. Extra 24. So this formula will automatically calculate any term you want to know. Let's try one more of those, and that's it. Okay, what am I missing that I need to know here?
The first term.
Right, I don't have the first term, so I got to work backwards to get it. So look at the pattern. How do you get from 6 to 12?
Add 18 from negative 6 to
Well,
12.
Multiplying by
it could be adding,
Right.
but because of the word geometric,
Multiply by negative 2.
it has to be multiplying. Yeah. So you multiply by negative 2 each time. So how would you go back?
Divide by negative 2.
Divide by negative 2. So that means the first term would be
3.
3. Okay. What comes right after the equal sign in a geometric sequence? 3, which is the first term. And r is what you multiply by each time. What's
So negative 2.
negative 2
And then n minus 1.
and n minus 1. Let's check it. If we plug in a 3, we should get a 12. And if we do, we did it right. What's 3 minus 1?
2.
2. What's negative 2 to the second power?
4.
And what's 4 times 3?
12.
Perfect. Yeah. So that formula will predict the terms in that sequence. So that's called a geometric sequence. Okay. Any question on that? Right. So that is the homework. Notice a lot of them just say odds. So 1 to 5, 9 to 13, and 17 to 27 are odd. 14, well, that's an even, and 31 as well. Okay, so I will pause that, and then I will put the list of topics that are going to be on the test in the video. And just a reminder, again, I will be after school today. So probably about 3:30 or 3:40.